Okay, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is to draw the Lewis structure of selenium dioxide. Okay, so when we want to find the Lewis structure, first we need to calculate the total number of valence electrons in this molecule. Okay, so in the case of selenium, selenium has 6 valence electrons, and oxygen also contains 6. And there are 2 oxygen atoms, so we just multiply this by 2, giving us a total of 18 valence electrons. So now let's write our selenium as our central atom. And then first let's start off by drawing 2 single bonds to oxygen. And now I'm just going to fill in all of my lone pairs. So notice that selenium doesn't have a full octet yet, so I'm just going to make a double bond with my second oxygen, and I'm just going to count out how many electrons I have so far. So I have 16 electrons out of the 18, so for the last 2, I'm just going to put them on my selenium atom. So now let's calculate the formal charges of each of the atoms. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So first let's do the leftmost oxygen. So I'm just going to write oxygen that is single bonded. It had 6 valence electrons, and it also has 6 non-bonding electrons. And there's a single bond with the selenium. So we have 2 bonding electrons divided by 2. So this tells us that our single bonded oxygen contains a negative charge. And in the case of our double bonded oxygen, it also has 6 valence electrons. Now it has 4 non-bonding electrons. And there's a double bond, so we have 4 bonding electrons in total, divided by 2. So this oxygen is neutral. And then lastly, let's calculate the formal charge of our selenium. So there are 6 valence electrons. The selenium contains 2 non-bonding electrons. And there are 3 bonds in total for the selenium. So we have 6 bonding electrons divided by 2. So 6 minus 2 minus 3 is positive 1. So that means our selenium will hold a positive charge. And we can also show resonance structures with our leftmost oxygen having the double bond, and our rightmost oxygen can have the negative charge. Okay, so these are 2 Lewis structures for the selenium dioxide. And you can see the junior tutor said the same thing, but I'm just going to say that the single bonded oxygen should have a negative charge. And selenium will have a positive charge. But the Lewis structures are correct. So I'll just say that this solution is correct. And moving on to question 2. The cyanate ion and the fulminate ion share the same 3 atoms but have vastly different properties. The cyanate ion is stable, while the fulminate ion is unstable and forms explosive compounds. Draw the Lewis structure for the fulminate ion, including possible resonance forms, and use formal charge to explain why the fulminate ion is less stable and therefore more reactive than the cyanate ion. Okay, so let's first start off by writing the Lewis structures for both the cyanate and the fulminate ion. So if we were to calculate the total valence electrons for both of these, since they have the same atoms and the same charge, oxygen contains 6 valence electrons, carbon has 4, nitrogen has 5, and because there's a negative charge, we add an extra electron to our count, so we have 16 electrons in total. So now let's do the cyanate ion first, which is OCN-. So this tells us that our carbon is our central atom, and I'll also draw the different resonance structures that can take place. So first, we can have a single bonded oxygen. Really, I'll draw it like this. And a triple bonded nitrogen. And the formal charges would be -1 for the oxygen and 0 for the carbon and the nitrogen. We could also have a double bonded oxygen and a double bonded nitrogen. This time our oxygen is neutral, carbon is neutral, and our nitrogen would have the -1 charge. And then lastly, we could have a triple bonded oxygen and a single bonded nitrogen. And if we were to calculate all the formal charges for the atoms, this oxygen will have a +1 charge. Carbon is still neutral, and this time our nitrogen has a -2 charge. But out of all of these structures, our first one is the preferred Lewis structure. Preferred has 2 R's. Oh, 1 F and 2 R's, I think. Since our negative charge is on the more electronegative atom, which is oxygen. Okay, so now let's look at the different Lewis structures of the fulminate ion. So this time we have nitrogen as our central atom. So this means that we can have carbon, nitrogen, and then a triple bond to oxygen. And this carbon would have 3 lone pairs. So if we were to calculate the formal charges for each of these ions, the carbon would have a -3 charge. This nitrogen would be +1, and the oxygen would also be +1. And that's how it has its -1 charge. Next, we could have double bonds all around. And in the formal charges would be -2 for carbon, +1 for nitrogen, and then 0 for our oxygen. And then lastly, we could have a triple bond in between carbon and nitrogen, and just a single bond to the oxygen. And this time our carbon has a -1 charge, nitrogen is +1, and our oxygen is -1. Okay, so let me just add a note here that the different resonance structures for cyanate have the least number of formal charges than the fulminate ion. So this is the reason why fulminate is less stable. Okay, so now let's see what the junior tutor said. Okay, so they just denoted what all of their terms mean. And they calculated formal charge. It looks like the structure should be here, but they're not. But let me just look at their formal charges. They have -1, 0, and 0, or what I'm assuming is cyanate. And then 0, 0, -1, and then +1, 0, and -2. And then I'm assuming this is for the fulminate now. -3, +1, +1, -2, +1, 0, and then -1, +1, and -1. The overall formal charge for all the structures is -1, which is consistent with the ion's charge. Since the cyanate has a lower magnitude of formal charge values than the fulminate, it is more stable. So all of the formal charges are correct. And the explanation is correct as well. However, the Lewis structures are not shown. So maybe it's like a technical difficulty, but I'm just going to say this solution is incorrect just so that we can see what the issue is. But it looks like they really labeled which structure is which and showed all the different formal charges, but we just can't see the Lewis structures for some reason. So on to question number 3. Draw the Lewis structures for the following molecules. A. Nitrous acid, HNO2. Let's calculate its total number of valence electrons. Hydrogen has 1, nitrogen has 5, oxygen has 6, and since there are 2 oxygen atoms, we multiply this by 2, and when we add it all up, we get a total of 18 valence electrons. So now let's draw what nitrous acid looks like. So this nitrogen will be bonded with the 2 oxygens, and then one of the oxygens will be bonded with the hydrogen that forms our alcohol group. And this oxygen will have a double bond. And now I'll just fill in all of the lone pairs. And then we can count out all the number of electrons to make sure that they equal 18. Okay, so each bond contains 2 bonding electrons, so we have 18 electrons shown. And everything is neutral as well. So this is the correct Lewis structure for nitrous acid. So now let's look at ozone, which is O3. Oxygen contains 6 valence electrons. And we have 6 oxygens bonded together, or 3 oxygens, sorry. So we have a total of 18 valence electrons. So let's show all the oxygens bonded together with a single bond. And I'll also draw in all of the lone pairs. So one of these oxygens will have a double bond with the other. And here, let's just calculate the formal charge. So let's calculate the formal charge of oxygen on the left. The number of valence electrons is 6. The number of non-bonding electrons is also 6. And there's just a single bond to this oxygen, so we have 2 bonding electrons divided by 2. So this oxygen will have a -1 charge. For the oxygen in the middle, I'll say OM. There's also 6 valence electrons. There's only 2 non-bonding electrons, and there's 3 bonds. So we have a total of 6 bonding electrons divided by 2. So 6 minus 2 minus 4 would just be 0. And now let's do the formal charge. Oh, sorry, this is 6 minus 2 minus 3 is +1. So the middle oxygen will actually have a positive charge. And now let's do the oxygen on the right. 6 minus 4 minus 4 over 2. So this oxygen is neutral. So we can have this as our Lewis structure for ozone. Or if we were to draw its resonance structure, then we can have the following. where our leftmost oxygen has the double bond. Our middle one will still have the positive charge, and the rightmost one can have the negative charge. Okay, so now let's move on to part C of this question. Lewis structure of acetaldehyde. For the total valence electrons, carbon has 4, hydrogen has 1, and there are 4 hydrogen atoms, and oxygen contains 6. So we have a total of 18. Oh, sorry, there are 2 carbon. Okay, yeah, so this is 18 valence electrons. And the name of the compound is written in a way so that we can kind of tell that one of the carbons will contain the 3 hydrogens, and it's bonded to a second carbon that is bonded to a hydrogen and a double bonded oxygen. So now let's double check and see if it has the same number of electrons. So each bond contains 2 bonding electrons. Okay, so this is 18. So this is the Lewis structure for acetaldehyde. Okay, so now let's see what the junior tutor said. They have the following for nitrous acid, which is correct. Ozone, they have the 2 resonance structures. They didn't specify the charges, but I'll just mention that in the comments. And they have the correct structure for acetaldehyde. So this solution is correct. For ozone, the middle oxygen contains a positive charge, and the single bonded oxygen contains a negative charge. But this solution is still correct. Okay, so question number 4 is to draw the Lewis dot structure for this CH3CN. So first let's find the total number of valence electrons. Carbon contains 4 valence electrons, and there are 2 carbons, so we multiply this by 2. Hydrogen contains 1 valence electron, and since there are 3 hydrogens, we multiply that by 3. Then nitrogen just contains 5 valence electrons. So if we add this up, we get a total of 16 valence electrons. So first I'll draw our 2 carbons bonded together, and then one of the carbons will hold 3 hydrogens, and the second carbon will be bonded with the nitrogen. So notice how both of these don't have a full octet. So the most reasonable configuration is if there was a triple bond between the 2 and a nitrogen having the lone pair. So now let's count out all the electrons I have so far. We have 2 in each bond and then 1 lone pair on the nitrogen, so this is 16. So this is the final Lewis structure for this molecule. So now the junior tutor said carbon has 4 valence electrons, nitrogen has 5. Both of them follow the octet rule. Hydrogen has 1, and it follows the duet rule. Okay, so they got the same answer. So this solution is correct. Okay, so question number 5 says to rank the following carbocations in order of decreasing stability. So a carbocation, or you can pronounce it like carbocation. Everyone says it differently. But pretty much this is a positively charged carbon. And we can have different types of carbocations, and they all range in stability. So for example, we can have a carbon that is bonded with 3 hydrogens, and it has a positive charge. And this is the same as like our methyl group. So I'll just call it methyl. And it's also the least stable out of all of the carbocations. Next, you can have a primary carbocation that is bonded with just another carbon group, and it can hold a positive charge. And it is a little more stable than the methyl, but still not as stable compared to a secondary carbocation, which, as you can guess, is bonded with 2 other carbon groups. And more stable than that is a tertiary carbocation. So it's more stabilized since it is bonded with the other carbon groups. But finally, the most stable carbocation you can have is something called resonance carbocation. So this is when there's a double bond that is beside our positively charged carbon. So I'll just call this resonance stabilized. And this is the most stable carbocation that we could have because the double bond will help delocalize the electrons and help neutralize that positive charge and make it a little more stable. So now let's look at our options that are given in the question. So we have the first option, which is an example of the primary carbocation. The second option is an example of a secondary. And the last option is an example of something that is resonance stabilized. So if we were to rank these, in order of decreasing stability, our resonance stabilized carbocation is first. So this is more stable than the secondary carbocation. So this one just has a single bond, but it is secondary. And then the least stable is the primary carbocation, which is CH2 and has a positive charge. Okay, so this is our order. Okay, so the junior tutor said that the stability of carbocations is determined by two major factors: the number of alkyl groups, or R groups, in resonance, and the number of alkyl groups attached to the carbon atom greatly affects the stability of a carbocation because the alkyl groups are able to share or donate electron density to the empty p orbital of the carbocation via a delocalization effect called hyperconjugation. Therefore, the greater number of R groups a carbocation has, the greater hyperconjugation there is, and hence the more stable the carbocation. Okay, so they ranked all the different carbocations you could have from methyl to tertiary. And then they said that a resonance stabilized carbocation, on the other hand, is more stable than a tertiary carbocation because electron delocalization is more observed in the cases of conjugated molecules. Therefore, in the case of the given carbocations in the problem, the arrangement of the carbocation in order of decreasing stability will be as follows. Okay, and this is because the first molecule is resonance stabilized, so it is the most stable. The second and third carbocation, on the other hand, are only secondary and primary carbocations, only hence the resulting arrangement was observed. Okay, so this solution is correct. Okay, so question number 6. What is the Lewis structure for H3O+? So this is the hydronium ion. So first, let's write its total number of valence electrons. Hydrogen contains 1 valence electron, and there are 3 hydrogens, so we multiply this by 3. Oxygen contains 6 valence electrons, and also this ion has an overall positive charge, so we know we have to subtract an electron from our total electron count. So these two will be added, but this one is subtracted. So 3 plus 6 minus 1 is 8 electrons in total. So now oxygen is our central atom, since it is more electronegative. And then let's just draw single bonds to all of the hydrogens and count out how many electrons we've drawn so far. So each bond contains 2 bonding electrons, so we have 6 drawn so far. Since we need 8 valence electrons in total, I'm going to draw the last 2 on my central oxygen atom. So now from here, we can calculate the formal charge of all of our atoms. So formal charge is equal to the number of valence electrons minus the number of non-bonding electrons. So this is all of the lone pairs minus the number of bonding electrons divided by 2. So now let's calculate the formal charge of one of the hydrogens. Okay, so all the hydrogens are the same. They have a valence electron count equal to 1. There are no lone pairs on any of the hydrogens, so the number of non-bonding electrons is 0. And all of them have a single bond, so this means there are 2 bonding electrons. We divide this by 2. So the formal charge of all of the hydrogens is just 0. So they're all neutral. So now let's calculate the formal charge of our oxygen atom. Oxygen has 6 valence electrons, and there's a lone pair, so we have 2 non-bonding electrons, and there are 3 bonds to the hydrogen, 3 bonds to all the hydrogens. So we have 6 bonding electrons divided by 2. So 6 minus 2 minus 3 is positive 1. So we know that our central oxygen is the one that has the positive charge. So now let's see what the junior tutor said. A Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. Drawing the Lewis structure of a compound may sometimes need some trial and error. However, we can follow some guides and rules in drawing it. Step by step, determine the central atom. Typically, the central atom can create the most bonds. Sometimes it is given in the formula of the compound itself. Step 2 is to logically arrange the atoms. Thinking beforehand how many bonds an atom can create can be helpful. And for atoms that follow the octet rule, the number of bonds an atom typically makes can be solved by subtracting 8 by the number of valence electrons of an atom. Yeah, that's another way of doing it as well. Step 3, we can connect our atoms, adjust if necessary. Step 4, check if the rules below are followed. If not, make the necessary adjustments. Step 5, redraw the entire molecule if needed. Hopefully you don't need to get to that point. And there's also some rules that we need to follow. Make sure atoms that follow the octet state strictly have 8 valence electrons. These are typically period 2 nonmetals. So we can have some cases where the element or the atom doesn't follow the octet rule. So some examples would be like boron or beryllium, where they can have like empty orbitals and still be like stable. Rule number 2 is to minimize the formal charges of the atoms if possible. Rule number 3, more electronegative atoms are given the negative formal charge if applicable. And lastly, rule number 4, make sure the sum of the formal charges matches the charge of the compound. So for our question, oxygen is more electronegative than hydrogen. So usually it wouldn't be given this positive charge, but in the case of hydrogen, since there's only one electron, or since there's only one valence electron, then it can't just like lose it since it's participating in the bonding. So this is why the oxygen would still carry the positive charge because it's bonded to 3 hydrogens. And then rule number 4, make sure the sum of the formal charges matches the charge of the compound. So again, we just have the one positive charge, so we're all good. And then they apply these guides to draw the Lewis dot structure of hydronium. Oxygen is the most logical central atom, since the hydrogen atoms can create one bond only. And then they drew the possible arrangement. And now they fulfill the octet state for oxygen. We must add one lone pair to the said atom. Okay, so they just double checked all the rules. And they showed the equation for formal charge. Okay. And the charge of the entire molecule matches the formal charge, and they got the same Lewis structure. So this solution is correct. Okay, so question number 7. Determine the major organic product for the following reaction scheme. So we have this benzene group that contains a chlorine, which is a good leaving group. So let's draw the first step. It reacts with two equivalents of lithium, and the solvent is the E2O. So when this reacts with the lithium displaces the chlorine, and also lithium chloride is formed in the process. So let me just write what happened. So organolithium compound is formed. Because the lithium, well, the organolithium compound can then act as a strong nucleophile. Okay, so now that we have a strong nucleophile, this can react with our acetone group, or this is an acetaldehyde, since it's at the end. So this is the structure of our second reagent. And then I can show how this nucleophile can come in and attack the carbonyl group, bringing the negative charge onto the oxygen. And then we get the following intermediate, which now has the negatively charged oxygen. This hydrogen stays the same, and then this is the methyl group that was in the acetaldehyde. And then I'll just show that this negative charge is stabilized by a positively charged lithium ion. So step 2, we had the carbonyl being attacked. And now for step 3, this reacts with H3O+, which in turn forms an alcohol group for our final product. So step 3, we have a protonation step under acidic conditions. Which gives us our final product, which is, if we try to name this compound, 1-phenyl. So the benzene will be treated as like a substituent, and we have 1-phenyl, 1-ethanol. The 2-carbon chain, and it shows that the alcohol group is on carbon 1. So now let's see what the junior tutor said. Organometallic compounds are compounds having at least one carbon metal bond that is formed when an alkyl or aryl halide is treated with a metal. The most common forms of organometallic compounds are organomagnesium, organocopper, and organolithium. These compounds are very strong bases and nucleophiles because the metal ion makes the R group or the carbon group electron rich, thereby making it highly reactive. In the case of the given reaction scheme, an organolithium will be produced after the first reaction. Note that diethyl ether was not involved in the reaction because it is only served as the solvent. Okay, so then they showed the formation of the organolithium compound. Being a strong nucleophile will then attack the carbonyl carbon of the acetaldehyde to produce the following product. Okay, and then next they, by acidifying the reaction mixture, oxygen atom will abstract one of the hydrogen atoms of the hydronium. Okay, so they showed how this will attack one of the protons, making water and our final product. In summary, the given reaction scheme will produce one phenyl, one ethanol as the major product. Okay, so this solution is correct. Okay, so question number 8. When the molar mass of acetic acid is determined in the solvents benzene, which is C6H6, or carbon tetrachloride, its molecular weight is 120 grams per mole. Calculate the molar mass of acetic acid from its chemical formula given above. The experimental molecular weight is 120 grams per mole in above solvents. What can you conclude about what form acetic acid molecules take when they dissolve in these solvents? Okay, so first we need to find the molar mass of acetic acid. So acetic acid, we can draw out the structure. This is the structure of acetic acid. And to calculate its molar mass, we need to find all the different molar masses of the atoms that are involved. So to find the atomic masses, we would just look at our periodic table. So for example, to find the molar mass of acetic acid, it's going to be 2 times the molar mass of carbon, since we have 2 carbon atoms in acetic acid, plus 4 times the molar mass of hydrogen, plus 2 times the molar mass of oxygen. So if we look at our periodic table, carbon has a molar mass of 12.01 grams per mole. Hydrogen has a molar mass of 1.01 grams per mole. And then lastly, oxygen has a molar mass of around 16 grams per mole. So if we add all these values up, we get a molar mass of 60.05 grams per mole. So the second part of the question, what can you conclude about what form acetic acid molecules take when they dissolve in these solvents? So if the experimental is equal to 120 grams per mole, if we divide this by the molar mass, we get around 2. So this tells us that acetic acid will form dimers in solution. Okay, so now let's see what the junior tutor said. Step 1, find the molar mass of acetic acid. They got 60 grams per mole, and then the molar mass is determined in C6H6, and the tetrachloride, carbon tetrachloride, is the double of the molar mass calculated from the chemical formula. It means acetic acid exists as a dimer in these nonpolar solvents. Yep, so this solution is correct. Okay, so question number 9. This asks to draw the Lewis structure for nitrogen triiodide. So first, let's find the total number of valence electrons in this molecule. Nitrogen contains 5 valence electrons, and iodine contains 7. And we have 3 iodine atoms, so we multiply this by 3, and we get a total of 26 valence electrons. So now let's draw our Lewis structure, skeletal structure. Nitrogen will be our central atom. And then I'm just going to draw all of the iodine atoms around it with a single bond. And then I'll draw in all of the lone pairs. Okay, so now let's count out how many electrons I've drawn so far. So we have 2 electrons participating in each bond. And so that makes us having... So now we have 24 electrons drawn in the structure, and I need 2 more. So I'm just going to add the last 2 on our central nitrogen atom. Okay, so this is our Lewis structure for nitrogen triiodide. And from here we can also calculate the type of molecular shape and electron geometry that this structure will have. So if we look at our central atom, which is nitrogen, there is 1 lone pair, and we have 3 bonded atoms. So from here, we can use our Vesper table, find out the type of molecular shape and electron geometry, hybridization, and the bond angles. So when we have 1 lone pair and 3 bonded atoms, this is the same, or this tells us that we have a trigonal pyramid molecular shape. We have a tetrahedral electron geometry. And the hybridization of the nitrogen is sp3. And finally, the approximate bond angles are around 109.5 degrees. Okay, so this is how one would use the Vesper table. So now let's see what the junior tutor said. Follow the following steps to draw a Lewis structure. Step 1 is to calculate the total number of valence electrons in the given molecule or ion. So they got 5 plus 21, so they got 26. Step 2 is to connect all the atoms in the molecule with single covalent bonds to draw a skeletal structure. Nitrogen is the central atom because it can form more than one bond, or more bonds than one. Or, sorry, that's iodine. Iodine, which just needs one more electron to reach xenon's noble gas configuration, forms only one bond. Therefore, nitrogen is placed at the center, and the iodine atoms are made to bond with nitrogen. There are 3 bonds in the skeletal structure, and each bond contains 2 electrons. Therefore, 6 are consumed for making the skeletal structure. The remaining is 20. Place the remaining 20 on the atom so that the octet of the maximum atoms gets filled. First, place the electrons on more electronegative atoms, then proceed to place them on the less electronegative atoms. Here, nitrogen is more electronegative than iodine. First, fill the octets of nitrogen atoms, and then fill the octets of the iodines. Okay. If they're not filled, then convert the lone pair into a bonding pair. But there was no need to do that for our example. And the next step is optional, but you can calculate the formal charge of all the atoms just to make sure that they have the smallest possible formal charges. So they included the equation for formal charge, number of valence electrons minus the number of bonding electrons divided by 2, minus the number of lone pair electrons, also known as like the non-bonding electrons. So for both nitrogen and iodine, they have a formal charge of 0. So the final Lewis structure is shown below. There are no non-zero formal charges, so formal charges are not marked on the atoms. Okay, so this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a thumbs up and a comment, and share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.